Our next speaker is Jamie Rhome. Jamie is with the NOAA National Hurricane Center. He's a storm surge specialist. He's also the NOAA rep for the Federal National Hurricane Program. He oversees the NHC's storm surge unit. And he also works internationally as part of a world meteorological team. He's the subject matter expert in improving storm surge predictions in Central and South America. What's that?
No.
Oh, that's not you. I'm sorry.
I got it.
So Cameron, especially at the end there, was the perfect segue for my talk, which will not be about science and technology, but will be about communication and how we've struggled in storm surge with the very problems that you in the climate community are struggling with now. I'm going to show you some of the things that we have done, which I think are finally moving the needle in storm surge for the first time in quite a long time. And then I'll leave it for you to see which of these ideas may or may not be useful to you. This will advance it?
Yes, that's correct.
So the topic of my talk is improving storm surge risk communication. I think everyone has probably noticed that storm surge has been thrust to the forefront in the last few years, notably by Irene and Sandy. It was at the forefront of everyone's thought in the Gulf of Mexico because of Katrina and Ike and Gustav and Rita. And now the Northeast has finally realized that hurricanes are a problem up here as well. Now, no matter where I go, it seems like everybody wants to run up to me and ask me, what's the forecast for this year? You know, wink and hint and tell me. You know, I know you can't tell me, but tell me kind of, sort of. Write it on a piece of paper or something like that. So since that's what everybody wants to talk about, let's just get it out of the way so we can move on. So as my introduction alluded, I am an international representative for NOAA to help other countries with storm surge. And I recently went to Japan, Tokyo, which is the National Hurricane Center of that part of the world. And this gentleman next to me is my counterpart. He's the storm surge expert at the equivalent of the National Hurricane Center over there. And the Japanese have a culture, a tradition. At the beginning of the year, they go to the nearest shrine and draw their fortune. And so we did this as part of me trying to understand and appreciate their culture. And both of us drew the worst possible fortune you can draw. So I submit to you, if two of the world's top storm surge experts both draw the worst possible fortune you can get, then somebody somewhere is going to get whacked this hurricane season. And that is my seasonal forecast. But on a more serious topic, if the #1 thing on your mind at this portion of the year is the seasonal forecast, you have missed the boat. It should be about preparedness. You should be coming up to me and asking me about the new products. How do I interpret them? What do they mean? When will they be available? What can I do to prepare better for this hurricane season? Because there isn't a person on the face of this earth that can tell you a hurricane is going to form and hit Boston this season. It can't be done. So we need to focus on preparedness. Now, what I did take from Japan was a very humble reminder about the perils of communicating. So this gentleman, and English isn't his first language, so this has grammar mistakes in it. He was doing this graphic to explain what inundation is. And note in the graphic, does this have a laser pointer? Yeah. Note in the graphic how he goes from a scenario where the water is normal and the land is higher. And this is not a problem, definitely safe. Then the water rises, but it doesn't get quite to the height of the land, so still safe. Then it gets about to the equivalent of the land, it's still okay. Now, at some point, the water gets higher than the land, and he deems this very dangerous. Now, I know you're all struck by the highly sophisticated nature of this graphic, stick figures and cartoons and this sort of stuff. And it's easy to laugh at this graphic, but I found it absolutely brilliant. Because we've taken something that people struggle to understand. No matter how many times I give a speech, no matter where I go, people struggle with this concept. That storm surge is all about the water rising higher than the land, and the difference between that and that is called inundation. And yet we cannot communicate this very basic principle wherever we go. I still have people come up to me and ask me, what does 5 feet above ground level mean? Seriously, people come up to me, educated people, scientists, meteorologists, and meteorologists within the National Weather Service still come up to me and say, what does 5 feet above ground level mean? Well, I stand 6 feet above ground level. So I was really blown away, and this graphic has been in every single talk I've done then. The media loves it, and some people have done an entire interview just on this graphic. It is called the Very Danger Graphic. All right, I want to talk quickly about what the National Hurricane Center does so you kind of have a concept. I think everybody understands what we do when an actual hurricane forms. We're doing forecasts, we're communicating, we're doing briefings, we're drinking coffee, we're not sleeping, right? Everybody can kind of understand that part. The other two parts of our mission that people, for whatever reason, haven't grasped yet is how many of you knew that storm surge is the reason this nation evacuates? All right, so let's go ahead and communicate that point. By and large, we evacuate in the U.S. because of storm surge, not wind. The U.S. is enamored with wind, but most people are dying in hurricanes from water. So we evacuate. Our evacuation zones are based off storm surge, and the modeling to drive those zones is done by the National Hurricane Center. To me, it's one of the most impressive parts of our mission, yet so few people understand it. And we also travel quite a bit to do awareness. I just checked my American Airlines account right before this. I'm up to 42,000 miles flown since January, traveling around, talking to individuals, raising awareness. These images on the right here are just to sort of give you an idea of what's at stake. This is the previous director, Bill Reed, briefing during Irene, current director, Rick Knabb, briefing during Sandy. You can look in the image here and see who's being briefed along with the cabinet. And in both images, you have me hunkered in a corner praying not to be relocated to a radar station in Alaska. Alaska always gets mad when I make that joke, but anyway. Now, to prove to you that storm surge is the reason we have evacuation zones evacuate, these are the recently updated evacuation zones for New York City. They released these about maybe a year or so ago. Now, they previously, if you remembered, had 3 zones, A, B, and C. They've since been replaced with 6, 1 through 6. These are theirs. These are not mine. This is not me. This is their graphic. But what I want to do is show you the modeling results that I provided them. The red here denotes the maximum theoretical inundation that can be achieved from the worst possible storm impacting the area, Cat 4. Look how close it aligns to their evacuation zones. Their evacuation zones, indeed your evacuation zones here in Boston, are based off the storm surge modeling done by the National Hurricane Center. And the way we do that is we do worst case analysis. Anybody read the book Black Swan? A great book. Write it down. Read it. It's my job to find the black swan or to envision black swans. And we turn this over to local emergency managers who then draw evacuation zones. So let me make a clear distinction here. I have nothing to do with your insurance rates. If you do not like your insurance rates, that's somebody else. Insurance rates are done by FEMA using the 100-year event or the 100-year analysis. Now, what would happen if we evacuated in this nation based off the 100-year event? You'd have a 101-year event. At some point, the evacuation zones would be too short. You'd evacuate too few people, and you'd needlessly put people in harm's way. This is why we do not use 100-year analysis, 100-year modeling, and your flood insurance rate maps for evacuation purposes. What happens when you do a 100-year analysis for critical decisions or infrastructure? What world event recently exposed the limits of 100-year analyses? Fukushima. They looked historically in time. That's how far the been, how far the water's gone. Let's build our nuclear facility right there. All of a sudden you have a 110 or 200 or 500 year event blows right through that and you're in trouble. This is why we do it this way. This is why we base life protective decision on worst case analysis. The flip of that, though, is if we did your insurance rates off worst case analysis, what would happen? Nobody could afford insurance. So about once a month, some bright person from DC will call up and say, you need to merge these two modeling approaches together. You know, we need to have one set of maps. No more insurance rate maps and storm surge maps. It's too confusing. Let's merge them. But do you see the perils of merging those two analyses? Somebody somewhere is going to get hurt. All right, so where we started. So when I came on board, I took this job in 2008, and I'm a sort of a history person. So I went back and looked. I know this is hard to read, but this is a memo from 1955, back when the Weather Service was called the Weather Bureau. Anybody remember the Weather Service was called the Weather Bureau? That shows you how old it is. And it's telling people for policy, it's telling our forecasters how to deal with storm surge, how to forecast storm surge. So it basically says that, you know, when it's a bad situation, you will communicate the water rise above normal tide levels. There it is, underlined. It's so important that they underlined it, above normal tide. And then it goes on to say you will use a range of values to denote the uncertainty. A range of values above normal tide level. You got it? This is the official forecast issued by the National Hurricane Center during Ike in 2008. 20 to 25 feet above normal tide. A range above normal tide. So I argue that the way that we communicated and dealt with storm surge went largely unchanged from 1955 until 2008. Anybody want to argue that society didn't change during that period? So it was clear we needed to make some very large and aggressive changes, and that's what we've been doing over the last 6 years at the Hurricane Center. Now, some people will say, if it ain't broke, don't fix it. People to this day still get furious with me that I'm moving away from above normal tide levels. They argue that people know what their tide levels are. They know that the public, who from focus groups don't even know what storm surge means, somehow magically knows what the house is relative to their tide level, can add the tide to the storm surge forecast, look up the elevation relative to NAV88 of their house, and perform the subtraction to deduce their flood risk. People cannot do this. And Sandy helped highlight the problems with this approach. So I've never seen a more butchered analysis of what happened in Sandy, even from officials. So we're going to talk about what really happened. This is the observed water levels from the Battery in New York City, which is the most commonly referenced feature. I've heard storm surge of 14 feet is what is most commonly referenced as what happened. And so this is 14 feet of water was at the Battery. No, that was not correct. So the blue line is the normal tide level, right? The red line is what occurred, and the green line is the difference. The green line is the storm surge, which is not 14 feet. And all of these are referenced to mean lower low water, which is a highly technical vertical datum. So everyone's confused, giving out numbers, different frames of reference. Some people think mean sea level, some people think mean low low water, some people think NAVD88, some people think ground. And when you don't specify your frame of reference, this is what happens. It gets confusing. And this is what actually occurred. It was 14.06 feet mean low low water, which is about 11.5 feet mean sea level, which is about 9 feet mean high high water, or about 5 feet above ground. The media quotes this number. But it's above normal low tide. Never mind that you have to raise the water 5 feet at the Battery just to get to normal high tide. So 5 feet of this is useless, right? There's normal high tide, is mean high high water. See, subtract 5 feet, it's 9. And never mind that there's a seawall there, that if you went to the Battery and jumped, you'd fall several feet before you hit the water. So part of this rise is just pushing it up the seawall. And at the end of the day, this is the amount of flooding that occurred above ground. But when you hear a number, when the public hears a number, do you think they can do this fancy datum transformation in their head? No, they cannot. When the public hears 5 feet, they think. So we need to talk in that way. And that is the thesis of this, this presentation, is how the Weather Service is transitioning from this to this, because this is much more intuitive to our audience. And there's a picture of the battery, just in case you're interested. Now, the other thing that happened in Sandy, and something this audience can certainly appreciate, is this uncertainty, right? 1 foot, 4 feet, right? You don't know which one. And you somehow got to go convince people to make very difficult and painful decisions, and you can't tell them whether it's going to be bad or back-crushing bad, right? This is the same problem we have in hurricanes. Emergency managers want a number, and we have to give them a range. They want a single number. You alluded to it. Get mad. Get mad that I can't give them an exact number. I have to give them a range. So if you recall, during Sandy, there was this point where models were taking it out to sea. Each one of these little blue lines represents an atmospheric model, or a scenario, if you will. So remember, there's a point where some of them were out to sea and some of them were back to the coast. Well, this is the point where most of the reliable models swung back to the coast. But still, look how much spread they are. All the way down here, closer to Virginia, and then all the way up into Connecticut. That's a big spread. And if you were to look at the different storm surge scenarios that could occur from each one of those lines, that's what the blue dot here represents. So look at the spread 2 days before for New York. 0, and these are in meters, 0 to 3.5 meters. So imagine if I go to New York. So you're going to get somewhere between 1 and 18 feet. Sound like a familiar problem? Now notice how that spread collapses as you march towards landfall, but it doesn't collapse until you get right at landfall. The other thing that came out of Sandy was the media seemed to think that we could have called what was going to happen in New York City with absolute certainty 2 days, 3 days, 4 days, that we were somehow asleep at the wheel because we didn't pinpoint with great precision exactly what was going to flood during Sandy. This is the same problem climate scientists have. Now, the yellow box here represents our forecast, our official forecast. The thing I want you to note here is at some point the forecast went up and went above all of the available guidance. What do you think happened here? This is human. This is a human. It goes to show that there's still value added by the person. That if models mysteriously could somehow perfectly predict everything, that we have no reason for the National Weather Service. We just automate the crap out of everything and send everybody home. And it's funny, but it's a serious topic. No model, whether it's our model or an academic model, will magically solve this problem. It's still very much human-to-human communication. And if you go back and look at the transcripts of Mayor Bloomberg, he will talk to you. You will hear him reference the Hurricane Center forecast is what prompted the evacuation of the city, largely because I was communicating directly with them. And that's the story that never got told either. So what was it that I said here that prompted New York City to evacuate? There was no numbers. There were no probabilities. There was no it could be this or it could be that. It was significant portions of your city are going underwater. Very danger. I dropped the physical science rhetoric and spoke to another human being in terms that they could understand. It wasn't 4 to 8 feet or 5 to 10 feet or 6 to 7 feet. There was datums, probabilities, none of that. It was Zone A is going to get flooded. Or I don't see any possible way that the subway systems aren't going to flood. And that's my challenge for this audience, is to start communicating climate change in straightforward and simple ways. Now, how did we come about this? How did we figure all this out? Because I assure you I did not slip and hit my head on the sink and somehow come to the epiphany, figure this out. This change was brought about by our customers. We flipped the paradigm. The traditional way the government likes to do work is you get a bunch of physical scientists in a room and they pontificate and somehow magically figure out what the world needs, develop it, slings it over the fence, and then we're shocked when it doesn't work. In this way, we flipped the paradigm. We went straight to the users via focus groups. Many of you participated in these focus groups up here and sort of said, what do we need to do differently? And this slide represents a culmination of the several years of discussions and working groups and surveys and this sort of stuff. But look at this, 18 focus groups. 18 focus groups, that's an impressive tally. Surveys, all sorts of customer engagement. That's how we came up with this idea that we needed to do something differently. And what the customer told us was that drop the geek speak, which we did in 2012 in our text advisories. Give us a straightforward and simple inundation graphic so that we can see what this means. And you need an explicit warning, which is 2015. So I'll be talking to you mostly today about this and how we got there. Now, when it comes to graphic design, I've never seen something so passionate with people as designing a graphic. Everyone's got a favorite color. Everyone's got a favorite background. For whatever reason, color is just almost as polarizing as anything else we could talk about in this nation. And so you have to put it to a test. You have to figure out a way to iterate through these different things and come up with the best solution. For example, do you use a simple background or do you use a complicated background? Well, complicated backgrounds are distracting. People start looking at their house in satellite image versus looking at the data. Do you use blue to denote something as water? Well, the polling showed that people had a hard time differentiating between the coast and the ocean when we use blue. Do you use a single color or do you use shades? Well, it turns out that even though this was my favorite and I can see it quite well, a lot of people could not see the different shading. Well, do you use color? What's wrong with this graphic? It's red-green. Majority of colorblind people are red-green colorblind. So you see the problem here is every time you think you got an answer, you don't. And one of the things that has come out of this for me is just how humbling it is to design a really good graphic and that I'm not equipped with the expertise to do it, that I have to reach out to other disciplines to do this and do it well. And we iterate it and we iterate it and we iterate it. And ultimately, at the end of the day, this is the final version that satisfied the largest number of our customers. Does everyone love it? No. Some people hate it, and they tell me about it all the time. But this was the version that matched the greatest number of people. There's a couple of things here that you wouldn't notice right off the bat. For example, have you noticed that the storm surge has been clipped over water? Now you do. Now, why is that? What does that do to your eyes when I take away all this noisiness over here? You don't look over here. You look over there. Where do we want people to look? Right there. What else? If we're saying that this is inundation or depth above ground and you show water over here, you're miscommunicating out of the gate. See what I mean? It's tricky to do a graphic. The other thing, the legend location turned out to be significant, and we used eye tracking to figure this out. Where you know what eye tracking is? You put somebody in front of a screen, you track where their eyes go. For example, if I asked you something about this blue area, your eyes should go right here first. If it doesn't, if your eyes go here, something's wrong. So we used all that technology to come up with this. Now, what's driving it? What's the science and technology behind it? It's driven by our probabilistic model. But anywhere in that graphic, did you see probabilities? No, because the public doesn't want to see probabilities. They don't understand probabilities. Most of our users don't want probabilities. It's driven by what we call a 10% exceedance. meaning we run our storm surge model thousands of times, and from that we can back out probabilities of an occurrence. And then we take the 10% exceedance, or the value upon which there's only a 10% chance that the actual storm will top it. So it's a reasonable worst case analysis. It's not a worst case analysis. That would be a 0% exceedance, right? And some people say, why don't you use a 50%? Why don't you give me your best shot? Well, do we really want emergency managers evacuating off something that's going to be too low 50% of the time? Likely not. So it's driven, one of the big technologies that's helping us do this is this new digital elevation model by NOAA's Coastal Services Center. If you don't have good topography, you guys know this in sea level rise when you're doing, if you don't have good topography information, you're really struggling. And we do all the processing with ArcGIS. There wasn't any sort of tools out of the gate that let us do this. And so how does this work? There's your storm. There's Irene, right? You remember this? There's the skinny black line. And if our forecast was absolutely perfect, we could run our storm surge model on that forecast and tell you with exact precision exactly what was going to happen and when it was going to happen. But in actuality, the storms have the potential to go to the right, to the left, and we run storm surge scenarios for all of these different cases. We use big, different size storms because nobody on the face of this earth can predict storm size. Nobody. If anybody tells you they can, run away from them. They don't know anything about hurricanes. So we have to use different storm sizes because we cannot predict storm size very effectively. And we have to iterate. And when it's all said and done, you end up with several thousand scenarios. The beauty of the model we use, which is called SLOSH, is we can run them on individual grids versus one large domain. This keeps the computing costs down. So what happens is we pick the grids that we need to run it on. Then we merge all of that to a single grid, which enables processing. If we zoom in over Southwest Florida, this would be like the raw data coming out of the model. And then we use GIS downscaling techniques to drive it to the resolution that is needed. Now, why do we do it this way? Because if we were to run a hydrodynamic model at the desired resolution, it would crush our supercomputers and take days and days and days and days and days. I don't have days in a hurricane. If the emergency manager calls me up and I tell them, I'm sorry, my model is running. Can I get back to you tomorrow? They would have me fired. I need to operate on the scale of minutes. So you run your model at a coarse resolution and process it or downscale it down to what you need. The downscaling takes 20 minutes versus what would take hours and hours and hours if you ran the model at that sort of resolution. And then when it's all said and done, we do this processing to clip the coast, smooth it out. You can't give people raw data. It's too noisy. It's too confusing. So you have to smooth it out and publish it to the web. So that's what we're going to do this hurricane season. There appears to be some sort of glitch in the slide here. So I'll blame it on the Mac. I wanted to quickly talk to you about this coastal issue. When you do not clip along the coast, look where your eyes are focused here over the water versus over the land. This is a much better job when you clip it precisely to the coast. Something as simple as that improves the readability of the graphic. And here's a couple of examples in other parts of the country. This is Houston, Galveston, which is very, very prone to storm surges. New York City, a little closer to home. And there's that still Mac bug in there. And then Charleston, South Carolina. This is just to give you an idea of what this graphic would look like if a storm were to form this year. It would be interactive. These are static images, but the actual would be interactive. Now, I'm going to end one quick thing. I got 1 minute left. I want to talk to you about why this is so important. Why are we dumping so much money and energy and sophistication into communication? These are the evacuation zones for Southwest Florida. All right? They're there. They're not ours. We help them make it, but these are the county's evacuation zones. The hardest decision an emergency manager has to make in a hurricane is who to evacuate, right? The most important thing they have to make is who to evacuate. Prior to this, we forced emergency managers to be storm surge experts to sort this out. But if I were to overlay this new graphic on that evacuation zone map, it becomes immediately clear which evacuation zones are most at danger. right? You don't need to be a storm surge expert anymore to imply risk or make sound decisions in a storm. And what used to take 24 hours, because I've been there with the emergency managers in the trenches during storms, can now be made on the order of a few minutes by simply overlaying the system on the evacuation zones. Now the emergency managers can focus on doing what they do best, which is protecting lives versus trying to be a storm surge expert. This is just to give you a quick glance of what it's, some of the takeaways here. It's an experimental product, experimental. Don't run out and bet the farm on experimental product. It's interactive. A lot of people think we've suddenly switched our model to like AdCirc or something like that. There's no model switch here. This is still using SLOSH. SLOSH will be the workhorse of the National Weather Service for a long, long time. We've just changed the way we present the data to the customer. There's no radical S&T, science and technology upgrade here. It's just reprocessing the data for better efforts. And we dumped a lot of money into the marketing and outreach. That's the other big thing that we did here. We didn't just sling it over the fence. So I'm going to end there out of respect for the time. And then I guess you want to do questions at the end since I bumped right up to the time? Okay.
Okay, let's thank Jamie very much.